Well, thank you for all coming actually on this cloudy, kind of misty day. It's actually appropriate to talk about cloud forest. As Yvette said, the official title of this talk really is Ecosystem-Based Management of Tropical Montane Cloud Forest. But maybe a more appropriate title would be, what are tropical montane cloud forests and why on earth are they relevant to the Department of Earth and Environmental Science and the Professional Studies in Environmental Science at UPenn in the middle of a nice urban city like Philadelphia. That's what I hope to talk to you about. And so what I'm going to start off is really talking about what are montane cloud forests and really this evolution we've been on for the last few years of trying to find ways to actually manage them appropriately and in some places to preserve them, and give some examples of how University of Penn students in the MES program particularly have actually helped in this endeavor. So what are they and why should we actually care about them? Well, it turns out there are about 18 different definitions of cloud forests, and obviously they have something to do with tropical mountains and something to do with clouds. But unfortunately, there's about 15 different definitions of them. The key part of all the definitions is that cloud drip is a major source of water. So as the clouds come into the landscape, they actually condense on the leaves themselves and actually drop down. And so the cloud processes, the cloud water, and how it actually influences the whole ecosystem is a major source of water and a major component of the landscape. We've seen them on many places. Many tropical mountains have actually been kind of intrigued natural scientists for over a century, and they tend to occur on the tops of mountains in the tropics. The bigger the mountain, the higher up they are, which has always been an intriguing question. They're also very good, high-quality water sources. So that's really one of the main reasons why we care about them. In fact, they're so important in some places, particularly for dry season supplies, that there are places in the Canary Islands in Chile, Guatemala, Africa, where people have actually put out nets, and there's enough water coming through that they can actually catch the cloud drip into these and send it downstream and actually give people water. That's actually happened in the Canary Islands for many, many years, places of Chile. But what turns out to be more important is the fact that they, even during dry periods, they actually maintain the stream flow in many tropical montane areas. They also turn out to be great barometers of climate change. And some of the two kind of poster children for climate change, Kilimanjaro and the Monteverde golden toad, actually live in cloud forest. And as things have gotten warmer, that cloud forest band is moved up. And as we've dried out and lost glaciers on the top of the Kilimanjaro, the Monteverde golden toad is another poster child for climate change. And it initially was shown that it lives in the mountains of Costa Rica and Central America, and its habitat is actually, they're decreasing in part because of drying. But the thought is that because they occur on the tops of mountains, and there's strong environmental gradients and rainfall and temperature and solar radiation, as you warm up the climate or cool the climate, you're actually going to migrate these bands up and down. And actually, in some cases, you could actually migrate them so far that you actually push the cloud forest out. So that because they're kind of at this interface between the landscape and the atmosphere, they should be good indicators of climate change. High quality water resources, barometers of climate change, they also turn out to be really biodiversity hotspots. And there's a lot of unique species, a lot of very high endemism in these areas, species that are only found in some places and others. And you can see this kind of general map of where the cloud forests occur, and then look at a separate map of biodiversity hotspots. Many of them are actually similar. Some areas are very unique patterns, even in the Loquillo Mountains in Puerto Rico, on the two mountain peaks, which are only separated by about 5 miles. There are two different species of plants that never exchange. And so, but they're also very old vegetation. We see this vegetation, the ones that are in Asia and the ones in the New World are actually fairly similar in terms of their habitat. So they're, in terms of their genetic, in terms of their background. And so their biogeography, the species that occupy them are unique, but they've also seemed to be around for a long time. They're also unique systems, and that's what's really intrigued ecologists and natural scientists for many years. Why they have very short, complex stature of 1 to 5 meters. This is a place in Hawaii. This is another one in Puerto Rico. Very short forest. There are places where you can actually take a baseball and throw it, and you're up here in these short forests, but where the baseball lands, you'll have forests that are 20, 30 meters in elevation, much larger trees. Why that is has always been an interesting thing. They have low diversity, but very high endemism. So not that many species, different species, at least of vegetative and trees. And they're fairly common, as I mentioned, throughout the tropics. But there's a lot of individuals, a lot of endemism, species that are only relatives that are only found in individual spots. They also have very low productivity. They grow very, very slowly, and we'll see some pictures of that later on. But as where tropics grow very quickly, the trees can grow. These grow on, an order of magnitude less. So there's always been an ecological question of why are these things so odd, even just up on the top of these mountains? Why do they grow so slow? Is it because of vegetation? Is it because of soils? What makes them so unique? So for a long time, they've been kind of interested, people have been interested in them for these biological reasons. It also turns out that when we really started looking at them, and I got involved in them in the late 80s, that some of the fastest rates of deforestation of all the tropics were occurring in these montane areas. And a lot of it had to do with local land use change, people moving up the mountains and clearing this land for both pasture and agriculture. Some recreation, because it's a very cool climate there, in some places in Asia and the Pacific, they were being cleared for golf courses because it's kind of a temperate climate, and in the tropics, it's a great place to go. Communication towers, we've lost a lot of cloud forests because of communication towers. And then this idea of environmental change. So these are local changes that have occurred that have lost them, and because these forests grow so slowly that when you do change them, it takes a long time for them to recover. Other areas, you can cut them down or make changes. They're very dynamic. These are, because they're so slow growers, it takes a long time for them to adjust. Climatic drying, as I've talked about, people have talked about the drying of the landscape, and as they move up, as things get warmer. And there's a lot of debate and interest about what's the major factor that's actually causing this deforestation. Is it local uses, local land use change in pastures? Is it regional, downstream conditions that have changed local weather patterns? We'll show some examples of that. Or is it really global change? Global climate change is actually causing it. So the question is, why actually try to conserve these things? And so once it was realized in the late 80s that they were being deforested faster than any place else. The question is, we should try to do something about it, or at least find ways to actually manage them in a sustainable manner. But like all things, you have to justify these reasons. There's competition for conservation funds. Why do these? Why not do other things? One reason is high quality water supplies. The other is this idea of dry season water supplies. In many places in Central America and Asia, and the Canary Islands is another nice example. It doesn't rain for part of the year because of the intertropical convergence zone, and they have a dry season, but because these keep on getting cloud inputs, they actually maintain some flow. So they're disproportionately important. Because of their unique biodiversity, they also have very low quality timber, and so it was thought, well, these are all good reasons why we should conserve them, not big trees. Very good carbon storages. They store a lot of carbon. The soils have a lot of carbon. Even if they grow slowly, it's so wet, it's like a wetland. Some of them are so steep you can barely stand up, but they basically have the characteristics of a wetland. So they have a lot of carbon. So that was another reason that we could all go ahead and do that, conserve them. And then the fact that they were small and isolated. And so if you think about back into the late 80s and the early 90s, there was a lot of concern about deforestation, trying to maintain tropical forest. It was thought, boy, these are all good reasons to do this. And you know, it would make sense to actually put your money into these areas. Well, like all conservation and all type of natural resources, we have limited amount of funds, and you can't, what is the justification for conserving these? Why tropical montane cloud forest, but why not dry tropical forest or wetlands? Or why not put the money into education or roads or health? There's a lot of things we can spend money for. Ultimately, you have to justify actually why you want to do that. And so that's really the part that's happened in the last 15 or 20 years, and where MES students and a whole range of them have been more or less involved. The first part of that we realized, that I'll show you some maps, we need to define and locate these things. We can't just say, you know, let's save tropical montane cloud forests. Where are they? We needed some type of map. We needed to get a better handle on what the threats are. Then the next step was, it's one thing to say, well, these are important water sources, but let's really quantify that, and I'll give some examples of that. And we've had a number of E&ES professional program projects looking at water quality, stream patterns. I'll mention some of those today. This idea of being good carbon sources, that also, it's nice to say, but you also have to quantify it relative to other resources. We've had some projects on that. And then ultimately this idea of payment for ecological services, that if these are of value to society in general to save them, then we should pay for those services and there should be some transfer of payment. But ultimately we should find some way to actually do that. And that's really, so if they really are these great sources of water and sources of biodiversity, they're helping the lowlands, so some of the lowlands should help burden the cost of actually trying to protect them. Sometimes there's a global resource in terms of the endemism, in terms of the species and the carbon storage. And so if these things are as good as we really think so, we should be able to make a strong argument for that, to transfer payments to ultimately save these. So the first part of this whole story comes to defining where they are. And this was the first map in 1994 that we actually made. And all these little clouds are where cloud forests are. It's not a very good, it's a terrible map actually. And I can say that because I helped make the map. And it's all we knew in 1994. We got a bunch of people around and that knew about cloud forest. We had some information. They all put little tacks on the maps on the walls. And unfortunately, there's 15 different definitions, but only 2 countries actually included cloud forest in their inventories, forest inventory. And those were actually the Philippines and Honduras that actually had them. And so, but we actually knew that if we don't have a better way to define them and to describe where they are and actually where we can actually focus our resources, we're not going to get any place. A couple of ways, we've actually come up in the last year and a half, actually, the final map has come up of all these. And just say a little bit of how it was done. The first map was made by just 100 people in this workshop, putting little dots on maps. And I think there's one up here, and I think there's one up there. And the next level was with the World Monitoring Center in England. They ultimately found 650 locations where we knew there were cloud forests. There was botanical descriptions of them. Someone had been there. So they took those and in individual locations, then looked at the elevations and looked at the rainfall and said, well, if there's one here and one there, more or less we'll make a map of where we think they are. That worked reasonably well. The next level is actually looking at cloud level data. So we have maps, global maps now of cloud cover, and so there should be mountainous areas in the tropics that get a lot of clouds, and so if you take all those layers and use your GIS skills and overlay them, you get an actual number. And then finally, the last level was taking cloud cover, forest cover, and then a hydrologic model of rainfall and uptake to better estimate where they actually occur. And that's more where the potential actually comes from. These are the ones we think are actually there. And a lot of this work has been done by colleagues, mostly Mike Mulligan out of the UK, King's College, and a whole range of people have been actually working on this. But so what do we find? So now we actually finally have a map of them that everyone agrees, and the first maps, they turn out to be, they don't occupy a big area. And again, they turn out to be only about less than 1.4% of all tropical forests. So some people could argue, well, who cares about them? They're so small. On the other hand, the conservation argument's been, well, they are small and they have these high qualities, so it does make sense to preserve them. Most of them occur in Asia, so out of all tropical mountains, actually they only occupy about 6%. There are other mountains in the tropics that get a great deal of rainfall and have other characteristics that are not quite the cloud forest type, and that turns out to be a big part of the overall management. There are different forests out there. The strict cloud forests only make up about 6%. Mostly in Asia, about 56% remain. Very little remain in Asia. Fair parts of the Americas, really the Andes, the Andean belt, some of them remain. Africa is where we have the least amount of information, less cloud forest. But ultimately, we've been able to define where they are. And that's really kind of the first question. If you can't define it, then it's hard to justify. So that work has gone on. It's really taken a number of years to actually come up, and even the differences between them some of the different models can be fairly significant, but most people are fairly satisfied with it. The next step is really this hydrologic resource. So the argument's been made that these are great resources, and articles in New York Times and UN people, oh, we got to save these for resources. Well, but there was very few actual water budgets that actually could justify that. And so that's been a lot of the next effort. The next two efforts on the hydrologic resources and also talking about their ecosystem services are much, much more local. So these are these big kind of global scale, and so we pretty much know these big areas have them, but we don't actually manage at this scale. We manage at a much smaller scale on this mountain range or in this country, and that's really where the water quality comes. And do they have the quantity and quality of water that's presumed? And what's intriguing about them is that, and many of my students over the years have helped do parts of this, that if you measure rainfall above the canopy, and then you measure rainfall below, you actually get a lot more water below than above. And that was the initial idea of cloud drip. And you can be out there and you can see it. And if any of you have gone to California and seen redwoods, you see some of the same thing. The fog comes in, condenses on the leaves, it starts to drop down. And so, cloud drip is really the difference between what the rainfall is coming in and what the throughfall is. So the very early budgets that were done in the 80s said, oh, well, that's about 8 to 10% of additional water that you're getting from this cloud interception. They're growing very slowly. Our evaporation term, if we think about our hydrologic budget, which when you take hydrology in the MES program or the MSAG program, you get to talk a lot about. Basically, it turns out that they're not evaporating that much. They grow very slowly. So these trees don't use that much water. And basically what comes in is rainfall actually goes out as surface runoff. And many of them in the initial sites seem to have a great deal of rainfall, 4,000 millimeters a year, which around here we get, what, 1,500 or something? No, much, much less. So great deal of rainfall. And again, it's because of this cloud interception happening on the surfaces. That was the initial idea. One of the key parts about that was that with deforestation, the reason why you're getting this excess water is because of these cloud drip. If you cut these forests, then you won't get this cloud drip, and you'll actually have less runoff. What most people forget is that we think forests are good for water, but they actually use more water than grasslands. They actually transpire more. They have more biomass to keep up. So in many places, if you cut down the forest, you actually get more water running off at the end of the year because grasslands grow. They don't use as much water when it's dry. They don't grow back where trees need to maintain it. So there have been schemes all over the world where, oh, let's cut down the trees because we'll get more water downstream. Other places like in Fiji, they've planted trees and all of a sudden they had less water downstream because the trees were using more water than the grasses. So it's really the surface water. Here was a really clear case where we thought initially that if you cut these trees, you're going to get less water downstream, everyone's going to be unhappy, you get more sediment, lower quality. Came out partly like that, and this was based on a few individual studies scattered around. Turns out that a lot of it has to do with measuring rainfall in these areas is really, really difficult. And a lot of the rainfall doesn't come vertically into a rain gauge, it gets blown horizontally. So part of this difference between getting more water down here than up here was because you weren't really measuring this properly, not because there was actually more water. And so that really got us scared. And so we've had many students over the years going out and trying to really pick apart this. And you can see how windy these areas are, especially on the taller forest. And then people have gone, we've done isotope studies and a whole range of things. At the end, it does turn out that cloud drip is important, especially in dry areas. So if you do studies during the dry period and the wet period, and what they actually, these elfin cloud forests, the ones that most of us have in our mind as the type of cloud forest, actually do get extra water. And if you plot mean annual precipitation versus mean annual throughfall, account for wind and have good rain gauges and only studies that have worked for years and for over a year, and students are out there very diligently, and they're MES students that have helped make some of these plots, some of these data points. They actually do have about 8% increased water. And isotopes show that. The other forests, as you go down on the slopes, they take up water. There's a lot of water that lands on the top of the canopy and then evaporates back up. And about 32% of it actually goes back up. And we see that in urban areas. That's one of the things why we like to have urban trees, is because we trap that water and have it run up ahead of time. So in the long run, basically, we have been able to show that they actually do, and that these actually take up about a little bit less water than people had thought initially, and that's actually very valuable. Water and rainfall is part of it, but it turns out that where the real money is in water coming off of the landscape. It's nice, the clouds and all that's very important to the ecosystem, but in terms of justifying it to people downstream, it's really how many gallons are coming off of these landscapes. And the question of deforestation and surface runoff of these is still a little bit up in the air. The forest part of it we have. The actual runoff, there's only been a few studies in the Pacific Northwest, in the west, which is not tropical, but one of the original studies, west, firs off of Oregon, where they have similar processes. It was clear when they cut the forest, they ended up getting less runoff because you had less cloud input. In eastern Mexico, it actually increased. Those are dry forests, again, a slightly different type of forest inland. No change in Costa Rica. So exactly that still is an unanswered question, and one that's actually very complicated and expensive one to do. But as you'll see, there's some students working on it now. In all cases, you get very high water, you get very high quality water. And what turns out to be important, especially from the hydroelectric powers companies, is that these are stable dry season flows. So when there's no rain, you're still getting clouds. They have a great deal of water stored in the upper soil profile. And so they're letting the hydropowers and the farmers use water all year round. So it seems to be it. And ultimately we come up, I won't go through all the details here, but we can map them regionally now. And we've realized there are different types. It's not just one type of cloud forest. They're tall and they're short, and each one has slightly different hydrologic characteristics. And it really comes down to this local distribution. It's great to have these large-scale maps, but we really manage on an individual small area. And so how do you actually go out there and define what type of forest it is? Is it upper montane, lower montane? We've come up with different groups. And then how do you identify them and then ultimately quantify those resources that are coming out? And that's where a number of MES and MSAG students are working now. So I mentioned one of the problems is that no one actually has ever used the term cloud forest, or just only very recently, and actually because of this work found actually has some classifications for it. But in national inventories, we don't really have maps of them. And so it's kind of the upper montane forest or the mountains up there, something like that. So the question is, how do you actually go out and identify them and know what those services are? Are they areas where there are going to be extra good carbon sources or extra water supplies? You can't go out and do detailed through fall studies and isotope studies. And just tell a quick story about this. When we first came out with this, a friend from the Costa Rican legislature said, okay, we buy it. We're going to protect these. I'm ready to write some legislation. What do I write? And, you know, and I was so happy, we said, well, we can tell by isotopes. And he said, well, you know, we can't go out and do isotopes on every farm. We have to have a simpler way to actually identify them. And so that's been part of the challenge. And the real question is, how do you go out in the landscape and say, like we do for wetlands, or like we do for riparian zones, we have some characteristics of these that you can go out and identify it, and then at least assign those some individual values. One of the ways, and actually a student is working on now, is by looking at the drainage density, the number of stream channels per square kilometer. So, and it turns out that tropical montane, if you look at rainfall versus drainage density, and this is actually a number of places, Dominica, and these are actually, the tropical montane cloud forests actually turn out to have slightly less streams than other places, even though they get a great deal of rain, 4 to 5 times as much rain as we actually get in Philadelphia, which always seems to me like it's a wet place. Can we use actually drainage density to help us map these? And also that has a practical implication, because if we can look at that, we can actually determine drainage density fairly well for remote sensing information. That, plus looking at the height of the canopy of the forest, you could actually go out and kind of identify these hot spots. Also has a whole set of implications for stream flow. Not having so much water, but not having so much streams means that water has a longer flow path to get to the channel, which means that's one reason why you have dry season flows. Whole interesting kind of questions of landscape development. So there's an MES student now actually is taking some data and looking at this question of tropical montane streams, mostly in the next data set that I'll show you from Puerto Rico, kind of going back and looking at what Walsh did and the drainage densities we've looked at to see if we can come up with some nice relationships to relate forest to rainfall to forest to actually stream flow. So what she's done is she's taken a number of GIS courses. We have this great data set that we've worked on for a number of years in Puerto Rico in the Luquillo Mountains. So it has forest type maps, it has elevation maps, it has geology maps, and it has soil maps. And by overlaying them, the game is to look at the drainage density, look at some simple topographic features that we can use to identify, we know what the forest types are there, can we come up with relationships and then use those elsewhere. So it's kind of a nice example of just using some data that we have in her GIS skills, and that was her interest, but also it's going to help us hopefully solve a bigger problem of how do we map these things at a better scale. Another example of MES and MSAG students dealing with this has to do with water quality. And we've said again, we know the water quality coming out, it's very good every time we go measure it. When you have a good forest there, it's very, very pure. A little acidic because it goes through a lot of these thick soils. But we also know that the riparian zones have a very important control on the kind of quality that you actually see in the stream. So if you take rainfall, and you measure rainfall, you get one water quality. If you measure water as it's going down the slope, you get slightly another. And finally, if you measure the streams, you get another. And it turns out that these thick accumulations of organic soils there have a strong influence on taking up nitrogen and a whole range of things. So Rafael Jimenez was a student who just finished last year. and he actually took a water quality model from one of his classes, the Siegfried geochemical modeling, and asked this question of how much carbon do you need, soil carbon do you need to actually reduce the nitrogen that's coming off of the landscape. And that also again tells us something about what part of the landscape do we want to actually preserve if we want to keep water quality, and what kind of riparian zones we actually need. And so it's another nice example of how these students have helped. So we've been able to define them, we've been able to locate them in a sense where they are, something about their hydrologic resources and rainfall, measuring it above and below canopies. The other key part that's always been talked about these is, one, is their soil resources. And from an ecological point of view, there's always been this question of why are they so stunted and small compared to forests? They're pygmy forests compared to ones downstream. And then we realize there are different types of cloud forests, but generally they grow very slowly. So it's this net primary productivity, how quickly they grow in their biogeochemistry. That's kind of been the scientific question. As people have talked about carbon credits, and there's a lot of people who've gotten dollar signs in their eyes and said, oh, well, these are going to be great places to protect for carbon because they have big, thick carbon supplies and they have this great water supply. And but again, you know, initially this was based on a very small set of data. Just to give you a sense, these are some of the smaller ones. These are very slow-growing trees, over a couple of 100 years old. They're only about this big. You can see very stunted canopy, full of mosses. Again, that's catching all that cloud drip. For years, people have wondered, why are these forests growing so small compared to the others? And there's a whole range, and we could talk about this for days. And believe me, I could talk about it for days. There are 9 basic mechanisms. Sometimes too much cloud, not enough light, too much rain. But about 6 of the 9 mechanisms actually are related to soils. The soils are too wet, they're too wet. Some of these areas are so steep you can barely stand up. But if you go and take a USDA wetlands classification, you end up being wetland soils because they're so saturated. So there's a lot of interest in understanding the soils. Again, that was something that not really understood, and so a MES student, Laura Roman, is part of one of her projects, went and started making a global compilation of tropical montane forest soils. They're all soil organic rich, they're not all histosols, they're not all peats like we kind of initially thought. They are different depending upon where you are. They actually have greater acidity than lower tropical soils. There was a lot of thought that the reason why these are so small is because they must be nutrient poor. And down in the valleys, you got these big trees, and they have great soils. These are poor soils because it rains so much. Turns out it's not actually the case. It does seem to be a case more of the wind and the rain and the saturated part of the soils. I won't go through it all, but in fact, they're not inherently toxic like people had thought. And we found a number of places, in the Philippines is one, and also in parts of Asia and Central America and the Andes, where farmers actually go up to these forests and mine them and get the organic matter to bring down to the lowlands. And again, because they have a lot of cations in there. So she put together this nice story about where these soils are, how they are. Then we went out to the forest and measured in a whole range of areas what the slope was, what the tree characteristics were, and then the soil characteristics. And then we came back, and then using her skills and statistics that she learned, was able to show, and I'm not going to go through all the statistics here, but it turns out that it's really slope and exposure and how much water you have on the landscape has had much greater explanation in determining tree height and productivity than the soils. The whole question, it was the soils, the debate of the soils versus climate and slope. Well, climate and slope actually have won out. Soils do explain a fair amount of the variance, but then they turn out to be related to slope and aspect. And so again, it's a nice kind of example of how she went out and used her skills. And actually, this just came out in publication last year. Okay, so the last parts of all this have to do with, payment for ecological services. So we've gone out, we've shown they're good water supplies. Again, because they're small, when you look at the whole basin, they don't actually add up to be a great deal, but they are valuable. The soils are actually useful, they are good carbon. How do we actually quantify this kind of payment for ecological services idea, and does this actually work? And this has been one in a larger context a number of MES students have worked on, not just here, not just in Puerto Rico, but elsewhere. And just to show you somewhat of an example of kind of this idea of ecosystem-based management, this is northeastern Puerto Rico where a lot of our work is. And all the areas in red here are actually forest. But all around it is fairly urbanized. And one of the questions come is, no matter how much money we spend and try to protect these areas, and they're well protected and they're fences, and they're these, you can't really protect them any better than we are. What about these regional issues and these global issues? If you're changing hurricane frequencies or if you're changing the land use from the bottom, how does that affect the forest? And again, this battle between local effects and regional and global effects, and that's really a kind of a key part of the overall picture. One of the things that, with help of a number of our, actually one's in this room studying sea surface temperatures, was around here earlier, we've started to look at, if you think about a cross-section of this mountain, so here's our cloud forest, and the sea breezes come in. All this used to be forest, used to be wetlands, used to be areas that were transpiring a lot of water, and so this air column here was generally pretty cool and had a lot of moisture in it. So as the cloud prevailing winds came in, they would meet, there was a lot of moisture here, and they got to their saturation point fairly early on, and there would rain out up here. The thought has come, well, what happens if you actually deforest this and turn this into an urban area? So now instead of having nice cool air above you, you have this hot, dry air coming off the landscape. As your clouds come in, they're going to have to go to a higher elevation to cool off and condense. And the argument's been made in a few areas where the clouds have had to go up so high they've just even passed over the mountain itself. And so, but that's, again, those were ideas that actually had never really been shown clearly. For tropical montane cloud forests, we know many of them actually occur along the tropical coasts, and this area is small, and the thought was, well, maybe it really doesn't have that much of an effect. Number of students have worked on this in the last couple of years, looking at sea surface temperatures, looking at regional temperatures, to get a handle on actually what happens. One, for example, looked at San Juan daily air temperatures and shows that they actually show a steady increase since the 1950s. So that's really what's happening on the coast here. You've made this very warm and probably have changed cloud base to some extent. What this peak is, we see a peak in the mid-80s that no one's been able to explain yet. We see it around the island. It's a mystery in a sense. It doesn't seem probably not a regional thing, but it's a local thing. And what we've actually come out with some surprises on all this is that actually you do heat this, you actually change the land sea breezes, and because this is warm, you actually get more wind in the evenings cooling off the landscape. But as that converges, it doesn't necessarily end up giving you more rain on top. And so this is kind of a developing story as we go, and there are different components of it. But the main point I want to make is that the local landscape, you can do all you want to maintaining this part, but if you don't think about the lower landscape, you can't do it. And that kind of comes to this idea of payment for ecological services. If these really are such valuable services, then there should be a whole range of values, and some of them can be monetized, some of them can't. Some of them are cultural values and a whole range of them. But water quality and low season flows, we've been able to demonstrate fairly well. One of the issues, so you try to, these guys are benefiting from what happens up here. One of the issues is what happens in the middle of the landscape has a big impact. So when we've gone into some areas and said, oh, well, you should be helping pay for the preservation up here, they say, great, but it doesn't make any difference to us because when it comes in the middle of the valleys, these guys all do the polluting. And so, you know, again, it's this landscape kind of perspective of things. Carbon credits and biodiversity, there have been a number of cases there where people have been buying up cloud forest. And when we were actually thinking initially that the lower people were benefiting from the cloud forest, now there's been a number of cases where it's shown the lower people are actually damaging the cloud forest because of because of urbanization, because of stopping migration of organisms. So instead of paying for benefits, some places, and actually in Costa Rica and Ecuador now, they're talking about paying for damages. What you've done downstream actually hurts upstream, instead of kind of vice versa. And actually, Beth Geingold in her MES capstone actually went to part of this, and she used her economic background to again ask this question: if you have pasture and you have forest, pasture is, well, forest gives you clean water, but it gives you less water. Pasture might give you more water because it doesn't use as much, but it gives you a lot more landslides and a lot dirtier water. So there should be some kind of trade-off there between how much water you get and how dirty it is. And as you get steeper and steeper slopes, you get more landslides. And so we went through a fairly simple model, and Beth did an excellent job on this, and looked at what slope do you get on the landscape where you start getting so much erosion from a pasture that really outweighs the cost of any increase in water you would actually get. And she showed about 12 to about 15%. At that point, you're getting so many landslides from pastures that you're causing so much damage, and you're filling up the reservoirs and causing so much problems with water quality that any gain that you would get from increased water is outwashed. And that's going to depend on where you are. And but actually, that's been used to help set aside some, in this case, the Puerto Rican forest water law, is that if you have forest on certain landscapes, if you clear them, then you have to pay extra because your damage is extra. And if you don't do it, you can actually keep them for longer time periods. But again, it's this kind of valuation trading issue. Quite intriguing. Okay, so we're almost for an hour here. What have we actually learned about all ecosystem-based management? Well, I am happy to say that a lot of this stuff is being used. So FAO, the Food and Agriculture Organization, which is in charge of monitoring the world's forest, now take cloud forest into consideration. It's one of their categories when you actually map. Not all, each country has their own protocols, but they recognize it. The UN recognized it very early on and talked about how great they were, but there hasn't been a lot that's been followed on that. Well, we know a slope aspect for soils and then the forest type. Those are kind of the level of importance. It's first the steep slopes and the strong aspects of the winds that are coming at you. That's what gives you these small elfin forest. The soils are next in that range, and then forest, they kind of interact together. But we've been able to quantify the relative importance. And then hopefully come up with areas like we have 15% slope or these aspects and this type of soils will give you some indication of how much water it's being taken off or how much carbon is being stored. There are different forest types. There are about 4 or 5 different cloud forest types, as well as lowland and upland. Each of them needs to be managed in an individual way. They also need to be, there are also local differences. Just something that happens in the Andes isn't necessarily going to work in drier parts of Mexico, and it's not necessarily going to work in Indonesia or someplace else. But locally, you can, by doing relatively simple studies, start to come up with these relationships. And that's really the hope, that then you start to manage on the landscape, having different ecosystem components. Drainage density, slope, soils, all those can be used to quickly identify the type of forest. And so my friend in Costa Rica would call up and say, well, you know, Fred, we can't do all these fancy studies here. We need something simple. Well, we're almost getting it ready for them. Slope and drainage density, and those are really the key things that need to be done. Dry season and base flow supplies, still some work on identifying the qualities of those, but that's becoming better. People are working on these more all the time. This idea of riparian zones and the high soil organic matter. Again, there's probably key parts of the landscape that if we can identify, they have a disproportionate influence on the overall water cycles or biogeochemical cycles. So our game is if we can identify them, and then you can put effort into protecting them, or to protect down regional things. And ultimately, you have to manage on a regional landscape basis. You can't just think about protected areas. You have to think about upstream and downstream influences, and coming up with ways to value these different services. And as I mentioned, not everything can be monetized. You can't always put a dollar value on these things. There's recreation values, cultural values, but at least we need to have the skills to at least to be able to put relative values on them, and then look on the landscape for where these actually occur. So this is just one example. I think I want to make you, hopefully you got some sense of how individual small MES projects, and some are class projects, some are capstone, some are undergraduate projects, how they can fit into a bigger project. And it's really not just in the cloud forest, and those are interesting places to work, not necessarily the easiest places, but we've had students do the same thing on the Wissahickon, or now we're trying to do more and more in the urban areas of Philadelphia. Or really, to me, what's exciting about this program is that people come and do individual pieces, but they actually fit a greater whole. And hopefully that's, hopefully I got some of that across to you. And also some appreciation for these really intriguing environments.